Relations. In our daily life, we come across many types of relations like father and son relation, teacher-student relation, brother-sister relation, a relation between the goods and its cost, etc. In mathematics also, we come across many types of relations like a line L is perpendicular to the line M. A triangle ABC is similar to triangle PQR. The set A is subset of set B, etc. Now, let us define what is a relation. A relation R from a non-empty set A into a non-empty set B is a subset of Cartesian product of the set A cross B. The set of all first elements of the ordered pairs in a relation R is called domain of the relation R. Similarly, the set of all second elements of the ordered pairs in a relation R is known as range of the relation R. And the set B is called codomain of the relation R. Types of relation. A relation R from set A to a set B is called an empty relation if there is no element in a relation R. That is, R is equal to empty set, which is subset of the Cartesian product A cross B. Universal relation. A relation R from a set A to a set B is called universal relation if each element of A is related to every element of B. That is, R is equal to A cross B. Properties of relations. Reflexive. A relation R in a set A cross A is said to be reflexive if every element is related to itself. That is, ordered pair A belongs to R for every A belongs to capital A, or we can say A relates to A. For example, the relations equal to, congruent to, parallel to or reflexive relations. Symmetric. A relation R in a set A cross A is said to be symmetric for every A, B belongs to R, B, A also belongs to R. Or we can say A relates to B should implies B relates to A. Relation parallel to is symmetric since the line L is parallel to M implies the line M is also parallel to L. Similarly, the relation congruent to is symmetric because the triangle ABC is congruent to triangle PQR, then the triangle PQR is congruent to triangle ABC. But the relation less than is not symmetric because 2 less than 3 do not implies 3 less than 2. Antisymmetric relation. A relation R on a set A cross A is said to be antisymmetric if A relates to B implies B relates to A if and only if A is equal to B. Transitive relation. A relation R in a set A cross A is said to be transitive if A relates to B and B relates to C should imply A relates to C. That is, if the line L is parallel to M and M is parallel to N, then L is parallel to N. So, we can say the relation parallel to is transitive. Now, consider an example of the relation perpendicular to. If the line L is perpendicular to M and M is perpendicular to N, L will not be perpendicular to N. So, the relation perpendicular to is not transitive. A relation R in a set A cross A is said to be equivalence relation if R is reflexive, that is A relates to A for every A belongs to A, symmetric, that is if A relates to B should implies B relates to A for every A comma B belongs to A, and transitive, that is A relates to B and B relates to C should implies A relates to C for every A, B, C belongs to A. Functions. Functions are special types of relations. Let us consider an example of books of different languages and its cost. Let A is equal to set of English, French, Telugu and Tamil books, and let B is equals to 50, 75, 35, 40, 100, 85 and 73 rupees. Since n of A, that is number of elements in set A, is equal to 4 and n of B, the set of elements in set B, is equal to 7, therefore n of A cross B, that is number of elements in a set A cross B, will be 4 multiplied by 7, that is 28. Therefore, the number of relation that can be defined from the set A to the set B is 28. R1 is a relation having the set of ordered pairs English, 75, French, 50, Telugu, 40, Tamil, 100. Similarly, R2 is equal to English, 75, English, 40, French, 35, Telugu, 100 and Tamil, 73. And R3 is equal to English, 50, French, 75, Telugu, 75. Let us analyze these three relations. All the three relations are giving an information about the cost of each books. For example, R1 is equal to English, 75 means the cost of the English book is 75 rupees. Similarly, the cost of French book is 50 rupees. The cost of Telugu book is 40 rupees and the cost of Tamil book is 100 rupees. Similarly, the relation R2 is also giving an information about the cost of each books. That is, cost of English book is 75 rupees. Again, the cost of English book is 40 rupees, which is impossible as the same book cannot take two values. Similarly, when you observe the relation R3, we can see there is no value, that is cost, is assigned for Tamil book. No book will be there without cost. In the above three examples we have discussed, we say the relation R1 is a function, but the relations R2 and R3 are not functions. Then, what is a function? The relation will become function if the elements in the first set will have unique image, or we can say no two elements in the set A will have the same image, or in other words, the first coordinate of the relation should not repeat. In our example, for the relation R2, English book has two costs. Therefore, it is not a function. Another point for the relation to become a function, every element in a set A must have image in set B. In our example, The third relation, Tamil book is not having any cost. Therefore, it is not a function. Types of functions. One-to-one function. A function f from a set A to the set B is called one-to-one or injective function if distinct elements in set A will have different images in set B. In this given example, the distinct elements of set A, that is A, B, C, are having different images in set B. In other words, for every A1, A2 belongs to A and f of A1, f of A2 belongs to B, and if f of A1 is equal to f of A2, then A1 is equal to A2. In this example, the elements 3 and 4 of set A having same image A in set B. Therefore, this function is not one-to-one. This is many-to-one function. How can we check the given function is one-to-one or not? Take two arbitrary elements x1, x2 in the domain of the function f. Substitute f of x1 is equal to f of x2 or f of x1 is not equal to f of x2 and solve the equation. If the solution gives x1 is equal to x2 or x1 is not equal to x2 respectively, then the function is one-to-one. Otherwise, it is not one-to-one. Onto function. A function f from a set A to the set B is said to be onto or surjective function if every element of set B is the image of some element in set A. That is, for every small b belongs to capital B, there exists an element small a in capital A such that f of A is equal to B. In this given example, f1 is onto since every element in set B is having pre-image in set A, whereas the function f2 is not onto because the element 3 in set B is not having pre-image in set A. We can also say that the given function is onto function if its codomain is equal to range. A function which is both one-to-one, that is injective, and onto, that is surjective, is known as bijective function. Inverse function. The inverse function for the given function f from A to B is f inverse from B to A. That is, the domain for the function f inverse is codomain of the function f, and codomain for the function f inverse is domain of the function f. Composite function. Let f be a function from a set A to B and g be a function from set B to C. Then the composite of f and g denoted by g composition f is defined as g composition f A to C given by g composition f of x is equal to g of f of x for every x belongs to A. A function f from x to y is defined to be invertible if there exists a function g y to x such that g composition f is equal to ix and f composition g is equal to iy. The function g is called the inverse of f and is denoted by f inverse. The main four basic operations, addition, subtraction, multiplication and division on real numbers can be carried out between two numbers. If we want to add more than two numbers, we used to find the sum of two numbers, then the sum of resultant and the third number. Therefore, the binary operation is the operation which carried out between two numbers or two elements. A binary operation on a set A is a function star which exists from the set A cross A to the set A. Properties of binary operations. Commutative law. The binary operation star on a set A is called commutative if for all AB belongs to A star B must be equal to B star A. Associative law. A binary operation star on a set A is called associative if for all A, B, C belongs to A star B star C must be equal to A star B star C. Identity element. A set A is said to have an identity element with respect to the binary operation star if there exists an element E belongs to A such that E star A is equal to A star E is equal to A, where A belongs to A. Let E be the identity element for the set A with respect to the binary operation star. Let A belongs to A. If there exists an element, say A inverse, in A such that A star A inverse is equal to A inverse star A is equal to E, then we say that the element A is invertible.